All right, so this is going to be our lecture on vision. So, what is vision? It's basically just your robot seeing things. CV stands for computer vision, and OpenCV is the easiest library to use. Easy OpenCV, typically also Easy OpenCV FTC, something like that, is an FTC library with all of the following resources we're going to go through during this lecture. And essentially, the goal is to take a feed from the camera and turn it into usable data that you can plug into your robot. So, an intro to some of the demo images we'll use in this sample and presentation is we have this A, B, C, D, E, F, G, the alphabet, all in different colors. You'll see why this is really important in a little bit. Then we have these three boxes. That's also going to see in a little bit. And into the deep stack, or with each one of the samples and a clip, just for an example, for an actual use case. And then we won't see this one much, but that's also one of the test images I've used. So, what are color spaces? Basically, you have your HSV, which is your hue, saturation, and value, which you can see on this chart, allows you to get some pretty high precision with your color detection. You have your normal RGBA, where the A stands for alpha, which is just the translucency of that color. And then the YCRCB. And I would recommend looking up your own chart for this. But what you can do is there's a luminance, which is your Y, color red, and then color blue. So it's really easy to detect colors. I typically use YCRCB more for FTC just because it's really easy to detect this blue space right here and this red space. Whereas if you used HSV for the red, you need to detect this, and then blue is just this. So there's different things you can do. Definitely use HSV for yellow, because yellow is nearly impossible for YCRCB. So what do these color spaces look like? So if we start at this alphabet image, and then we turn it to YCRCB, you can see that some of it's really the blues, or I guess the greens, and the blues appear the most, as well as some of those reds, like this BH right here. Those ones appear a lot more. So do the DJPVs, all those ones. So that's why you use this, is to kind of just show you. The reason I included this slide was to show the differences, not at all to show you what it looks like in a different color, but just to show you how some colors appear more vibrant in certain color spaces. So then we have an example of the HSV, which you can see the blue a lot more in here. It's pretty hard to distinguish this entire block right here between the yellows, the oranges, and the reds. So that is one of the downsides of HSV. So switching color spaces, this is going to be a Python code, but it translates almost exactly from Python to Java. And this will be one of the very few times I say use AI, but use AI to switch from Python to Java because it is really good at doing that. Essentially, how this is formatted is we start with the BRG. We want to go to gray. And that's what gives us this image right here, is our grayscale image. So what is a scalar? A scalar is defined like this, where we have three different values in the scalar, and it all depends on the color space, right? So if it's for RGB, the scalar would include an R, a G, and a B. If it's for HSV, you guessed it, that's what the three are. It's literally just a definition for color. So many times for color thresholding, as we'll see later, all it is seeing how it would affect it later. Sometimes we have a low threshold and a high threshold, so we can take all colors in between. And these are both scalars. So now moving on to matrices or mats. This is the way to create a new mat. It's just a matrix of pixels. So if you represented, your full HD image of Mario here, and you broke it down into pixels, and you broke it down into pixels again, and you keep doing that, that's what it's doing. And it's literally just the resolution of the image is the dimensions of the matrix. So if we want to go through and blur an image, we're going to start off again with that alphabet image. And we'll do a Gaussian blur with this 5, 5, and a 0. And we'll see how that changes because these two parameters must be odd. But you can see it's a little bit more blurred here just because we have larger dimensions for our blur. And then here we have a larger amount of iterations. So it blurs it, and then it blurs the blur, and then blurs the blur. So you can see how you can really just play around with it, and there's no one image detection model for anything. But this is just an example of what a blur would do. Now for eroding, we're going to start off with that same thing. This just makes most of the colors more prominent and makes it all kind of big and clunkier. But we define this kernel, which is an array of ones. It's a 5 by 5 array of ones. And we plug that into the erode with one iteration, and it'll give us this. And you may ask, why would we ever do this? And it's sometimes helpful for, especially for looking into the future for the BioBuzz season. It'll be helpful to detect that one ball in the sea of the field to just kind of know exactly where it is. Then we can see how this gets changed. If we do the same thing, we up these both to 9. It looks much clunkier. And then as soon as we increase the iterations, it becomes nearly unreadable because it's eroding it again and again and again, each going off of the last image. So it makes it look really bad really fast. So in general, make sure what you're doing is not going to make your image look like whatever this is. So for dilation, this is essentially the same thing as what erode does, just in the opposite, right? So instead, we're able to get these kind of images where they're kind of blurred, but you can see it's much more abstract, and all the colors are much more vibrant. So you can really tell the difference between each color, especially in this first image. You can really tell the difference. And that'll help the computer and the computer vision to tell the difference better. So then we go into a bitwise OR and a bitwise AND. It's the exact same thing as an AND and an OR gate. It's just bit by bit. So for instance, if we have number 1, which is 10101 and 11100, then an AND would be only if these two are both true, which, yeah, it is. And then an OR is if either one is true. We can go through and do the ORs really quickly just because we need to drop down all the ones. And the AND, this one could be a 0, 1, 0, 0. Okay, cool. So we've done that. Now what does that give us? Well, as we'll see in a second, you can make a color threshold of only the yellows and a color threshold of only the blues. And then you can bitwise AND them together. And you will get this, where we have a color detection model that includes both. So color thresholding, we've been talking about it for a little bit. Let's get to it. So taking that same alphabet image, we're running this code right here. Again, this is in Python, but it's able to extract all the reds. That's cool because that's what FTC uses. So why not? That's perfect for us. So as you can see here, we have a lower red, which is that lower scalar. And then we're going to have an upper red, which is going to be that upper scalar. And then we bitwise and our initial image, right? So our very first image that we ever took, which is our alphabet. And then we mask it with that mask that we just created by this CV2 in range function. And the CV2 in range function is going to take our HSV image, our lower and our upper, and it's going to black out all of this. So then we can only see the red bits. So for more examples of this, you can see it gets yellow is really hard to detect. So it gets a little bit weird in here. Blue is really easy, as you can tell. It's very, very easy because white doesn't affect the blue spectrum nearly as much as it does the yellow. So something to be wary of. Every color you have to detect is going to be different. So test it a bunch. There's this thing called Paper Vision, I think it's called, and it's just a simulator for this. So that's a good resource. But then for contours, this is using the red detection model that we just had as a basis. And then what we're doing is we're taking the largest contour, which is that B, and we're changing it to blue. So the nice part about this is we can find all of the contours in an image, and then we can take that image array and we can draw the contours on it. So we have our original image just with contours. And what this does is, you know how if we had from that last slide where we had our color thresholding, we had our B in here. Well, now if everything else is black, well, then this must be the contour around the B, right? So that's the way it's able to find that. It's also useful to do it in grayscale sometimes, but really all of this code is just copy and repeat. So contouring you can find online really easy. So if we want an example of color thresholding plus contouring plus bounding boxes, we can get this beauty of an image where it shows us where our two samples are from that one of those first images we were detecting. And we're good. Look at that. So if we want to do something a little bit more different, we'll do a submat, right? This top part is the one in Python where you can see it's just selecting a little bit of the image array as a region of interest and outputting that. But essentially the idea is take a larger image, right? That could be that big and only take a little bit of it. And then this is the way to do it in Java. It's just making a submat where we copy over the region of interest. So if we want to do a little bit more with this, we can take the average of a submat. And what this allows us to do is it allows us to create these kind of diagrams that show, you know, oh, this little area has an average color of this, or this top area has an average color of white. Like, it's very easy to do that. But it's also really easy. Like, and all you do with that is if you have a sub 1, right? Let's just say sub 1 is this. Well, then all we do is we say mean is equal to CV2 dot mean of sub 1. And we have the average color of that entire block. So that's pretty cool. And then for this one, all we did is take a region of interest and project it up to this circle, project it up to this circle, project it up to this circle, so we can see the average of all of these different green submatrices. So one of the reasons you would ever use this is for in the center stage challenge, right? You can see it better on the blue side. 3 little tape marks. Okay. And you could have your scoring element on one of the three, and that was randomized, right? So we would have it here, here, or here. It would be one of the three. So what that would let you do, and why we chose a big red cube, is because we could see the center one and the right one. And basically what we did is we took the color average from each of these submatrices, right? So our center and right, both are submats. And if the color average was at a certain threshold, we could tell that the object was there. Now you may say, what would we do if it was the left one? Right, because we have our center and right. Well, if it wasn't in the right and it wasn't in the center, well, then it must be over here on the left one. So we could also detect the left, even though we couldn't see it. So, some tips. Use AI or other resources for this. They really excel at this image detection code and switching from Python to Java. I would recommend to make it in Python if you know Python, and then switch it to Java because it's really almost a direct translation. And then FTC has great examples of incorporating these full processors inside of op modes. So I'd recommend you look into that because it is a little bit more of a process to make this an actual op mode and an actual processor, just because FTC has certain requirements for those. But other than that, it's a pretty simple thing to do. There's a lot of stuff you can do with this, and there's a lot of really cool, just kind of random stuff you can do with this as well, just to make your vision systems better. But I hope this was useful, and thank you for watching.